First of all, I would like not really thank the organizers for obvious reasons, but I would like to thank Fernando personally for his help in organizing this event, and I also would like to take this opportunity to thank IMPA for both the financial support and also for the administrative support with the Departamento de Atividades Científicas e o pessoal aí que cuida de filmar as palestras, que eu acho uma coisa muito interessante. Então, muito obrigado a todos pela ajuda. Então, isso aqui é uma palestra que é a continuação da primeira palestra no evento que o Gérard Besson deu. Na realidade, eu vou essencialmente falar de uma das coisas já que ele falou. Esta conferência vai ser realmente independente. Também não... desculpa. Yeah, sometimes I have some difficulties with the switch in my mind. Okay, sorry. Okay, sorry. Yeah. Okay, so essentially, I mean, the talk will be essentially independent from what Gérard said, and somehow this will not really be a mathematical talk. What I would like to do is to advertise some problems. It turns out that we have, as Gérard mentioned, we have worked on these embeddings by eigenfunctions some time ago, and our motivation was essentially to have analogs of Gromov compactness, pre-compactness theorems in the analytical framework. And our attention was drawn on these embeddings by eigenfunctions by people from other communities, and essentially by Jovan Tavares from the geometry processing, and also by Radu Oro in Grenoble from data analysis. And that's more from this perspective that I would like to talk on embeddings by eigenfunctions. And with Gérard, that's a kind of research project that we are beginning now, and the idea is somehow twofold. On one hand, we think that we might be able to prove things that would be useful for the people who look at embeddings by eigenfunctions in an applied context. And on the other hand, we think that the people who work in this context, they have a different point of view, which might be interesting from the point of view somehow of inverse spectral geometry. And so that's essentially the general idea of the talk. And so, as I said, I mean, that's essentially a beginning research project, so there will be no real big theorems. But I think that there are some ideas which might be useful in this to look at. So the first part of the talk, I will essentially remind you of some basic results in spectral geometry, and then I will switch to the transparencies, and I will essentially show you some pictures I took in the papers and explain to you the mathematics that are behind these pictures. Okay, so the first thing I want to do is just to fix some notations. So in this talk, I will only consider closed, connected, Riemannian manifolds, and maybe essentially surfaces. But so I won't consider the boundaries. I mean, manifolds with boundaries, and connected is just needed at some point, but that's not so important. And of course, I have the Laplacian, and as some people, my Laplacian is positive, it's not negative, but that's not so important either. And then I will just, for simplicity, I will define something, and what I will call a complete orthonormal set, spectral set, And by this, I mean that I am considering the eigenvalues and an orthonormal basis of associated eigenfunctions for the Laplace-Beltrami operator. And of course, this is orthonormal. Okay, so now the main tool I will be using is the heat kernel. So let me remind briefly some results which Gérard mentioned in his lecture. So we want to solve the problem du dt plus Laplacian u equals to 0 in limit when t goes to 0 of u of tx is some given function f. And essentially what the theory tells you is that there exists a unique say infinity function ktxy such that u of tx is given by the integral over m. I mean, we can assume f to be continuous just to make things simple by k of txy f of y d mu y. Just here, put g just to remember. This is just the Riemannian measure. Okay, so let me just remind you some properties, just not to forget anything. I will. Okay, so the main properties. The first property, very important property, is that. I mean, the first important property is that this is infinity, of course. I mean, that's... but something that I will use later on is that this function is positive. It is also symmetric in x and y for all x and y. And we have the semigroup property. Maybe I will use it, so I will write this. S. So if you take this kernel at two different times and you integrate with respect to z, what you get is the kernel at time t plus s and x, y. So this is essentially this is the semigroup property. Okay, and okay, so now, Now the third ingredient that we will use is that you can write this function, you can expand these functions in terms of this orthonormal basis. So you have the formula that k of txy is just the sum. Here the index goes from 0 to infinity. I from 0 to infinity of e to the minus lambda I t phi a of x phi a of y. Well, I mean, here, just to make things clear, I mean, here you have to fix an orthonormal basis, and when there are multiplicities, for example, in each eigenspace, you have an orthonormal group. But here, of course, I mean, when you look in an eigenspace, what you have here is the projection on the eigenspace. So that this here does not really depend on A. Okay, so this is just to make things clear. And something that is useful in this context is the same function but which you integrate over, you look at what happens at the diagonal and you integrate over your manifold. And of course, because you took an orthonormal basis, what you get is this function which only depend on the eigenvalues. Okay? Okay, so now okay, so what is the prototype? Well, the prototype for the heat kernel is what happens in the Euclidean space. Of course, the Euclidean space is not compact, but so you can look at the following function. Let me just write this like this. So this is the minimal heat kernel somehow on the Euclidean space. And for example, if you look at a torus, then the heat kernel for a torus will be this here. Let me write this like this. Okay, or if you want, this is just x minus y minus gamma squared, if you want to see that in terms of the length of a point in the space. Okay, so of course, I mean, in this case, you get the heat kernel of the flat torus just by taking the mean over the group of the heat kernel on Rn. Okay, well, in general, of course, you don't have such nice expressions, and the idea to look at the relation between the spectrum, which is here, and the spectral data, which are here, and the geometry is to find another expression for the heat kernel. Okay, and so the idea, as Gérard already explained in the first lecture, is that at a very small size, infinitesimal size, a Riemannian manifold looks very much like Euclidean space. So the idea is to take this term on a general Riemannian manifold as the first approximation to the heat kernel. And so the idea is to somehow, for x and y small enough, for the distance between x and y small enough, is to write this kernel with this first term, and then to make some corrections. And the corrections, I will continue here, the corrections you write like this. Okay, so first of all, there is one difficulty. The difficulty, of course, is that the Riemannian distance, even squared, is not infinity on the manifold. So that's the first difficulty. And but okay, just forget it for a minute. And the idea is you just take an expression like that, you apply the heat operator, and then you want to kill as many terms as you can. And you want to use, there is one property I forgot to write here. Of course, say 1 prime, is that the limit when t goes to 0 of k of t x y is just the Dirac measure at the point x. When you consider, well, that's not really correct. I mean, let me just write something which is better. So this I view as a density. I put here the Riemannian measure, and then I have the convergence of the measure to this Dirac measure. Okay? So if you use this, somehow this will tell you what u0 of xy is. And then so that's the initial step. And then you apply the heat operator here, and you want to kill as many terms as you can to make the result as small as you can in T. And this will be determine these coefficients, these functions, recursively. Okay? And so this will be well defined for x and y small enough, and then you have to do some extra work to have the expression. But say we have something like that, at least for x and y small enough, and this implies, for example, something that we will use, that k of t xy, no, xx, has an asymptotic expansion so I write this as an asymptotic expansion, and these here are of course the values here on the diagonal. And for example, this first term here is 1/6 of the scalar curvature of M at the point X. And the other terms are rather complicated to compute, but essentially so this is called the Meenakshi-Sundaram-Pleyel expansion, and essentially using the universal expansion for the exponential map, what you prove is that these functions here are universal polynomials in the curvature and its covariant derivatives. And technically you should be able to compute them, but that's very difficult, in fact. Okay, but we have this. And of course, I forgot to say something here. So n here is the dimension of the manifold. Okay? Okay, so I think I said the important things. Okay, so I will need essentially these results here. You can forget the prototype over there. Okay, so now I would like to introduce what the prototype of embeddings by eigenfunctions. Okay, which Gérard also explained very fast. So I will say a little more. So that's a prototype embeddings by eigenfunctions. So that's a very particular case. So I will take as Mg what we call the compact rank 1 symmetric space. So that's, let's say, a sphere with the canonical metric, or a projective space, again with the canonical metric, where you can take the real numbers, the complex numbers, the quaternions, and in dimension 2 you also have the Cayley plane. So it turns out in these cases that if you take lambda an eigenvalue, of the Laplacian on this space, then it turns out that the eigenvalue has big multiplicity. And it's so big that if you take the corresponding eigenspace, let me denote by the dimension by n plus 1, and you can take an orthonormal basis of eigenfunctions in E lambda, then you have the following theorem. So you have the following theorem, which I think goes back to Takahashi, but I'm not sure whether he was the first one to do this kind of things or whether he only noticed that it is minimal, but let's say that's Takahashi. Well, it should be, if that's him, it should be around 1967. But okay, so you can, okay, let me assume that this eigenvalue here is fixed. And you can look at the map, which sends the point x in your symmetric space to phi 0 of x till to phi n of x. And the result is essentially that the image of lambda, in fact, lies in the sphere with radius, let's say, r, and r is n plus 1 divided by the volume of M, 1/2. So the reason for this is that you have so many symmetries that in fact, when you evaluate, when you compute phi 0x plus until phi n of x, this does not depend on x. This is a fixed number. So this is because you have so many isometries. So that's the first thing. The second thing is that that's essentially an embedding. So that's unless M is a sphere and lambda of M is a projective space. So essentially this happens when you consider an eigenvalue here with symmetric under the untypable map eigenfunctions. So that's when you have even functions on the sphere. So let's say that's essentially an embedding. In fact, it's minimal if you put the induced metric, and what you have is that the pullback metric, let's say G naught, the pullback of the canonical metric is just a constant times the original metric, and the constant is lambda r squared, which is here, divided by n. Okay, so that's a very particular property that if you take these symmetric spaces, in fact, you can realize them, maybe with a small ambiguity here, isometrically or, I mean, homothetically in a Euclidean space by eigenfunctions. Okay, and somehow the idea is to reproduce the same result for a general manifold. And of course, this will not, I mean, the same theorem will not be true, but we hope to have something similar. Okay, then, okay, later on I will, okay, I will skip something here. I wanted to, okay. Okay, let me just erase this. A small. So the theorem that we can state. Okay, so let me now take a general Riemannian manifold. And let me take a complete orthonormal spectral set, and let me define for T positive, for any T positive, and with this given set, let me define the map which goes from M to L2. Well, this is the space of square integrable series. Let me put 1 to infinity here. And the map is x goes to something here. And here I take e to the minus lambda I t over 2 phi I a of x, I from 1 to infinity. I just forget the constant eigenfunction, which is not so interesting. Okay, so essentially what we do is that we have this map which, to a point in the manifold, associates a point in this universal L2 space, and this is done with I mean the initial data somehow is this orthonormal complete set. So the theorem, so that's a theorem with that's a null result, in fact, with Besson and Gallot, tells you that so the first thing is that psi t a is an embedding for all positive t, and the second statement tells you that psi t a, the pullback by psi t a of the canonical scalar product of L2 is the original metric G plus what is it, T over 3. So that's 1/2 of the scalar curvature of G times G minus the Ricci curvature of G plus some error term. Okay, so essentially, I mean, this part is essentially because the eigenfunctions separate the points. That's essentially the idea. And this point here, you have to work more. And this comes essentially from this expansion that you have to differentiate with respect to x and y and look at what happens on the diagonal. And then you see the metric which appears essentially when you differentiate this. Here you have the derivative of the distance from the, I mean, with respect to x and with respect to y. So you take first derivative, but with respect to one variable and then the other, and you look at this on the diagonal. That's essentially what gives you the first term here. And well, if you really want to have this, then you need two things. You need, first of all, a constant which only depends on n, which is not so important, and you need this term. And this is because here you have this t to the minus n over 2. When you differentiate, you will be an extra term coming out. And if you want to kill this behavior when t goes to 0, you have to multiply by this. So if you really want to have 1 in front of g, then you have to put this power here. Okay, so that's a kind of dual thing, because you see that when t goes to 0, the image shrinks to a point. But then the metric is reasonable. If you don't want the image to shrink, then the metric will not be reasonable. But anyway, the important thing here, so let me state this maybe as a corollary here, is that if you are given a complete orthonormal spectral set on M, then you know the metric. Okay, so somehow this tells you, this tells you that if you know enough of the spectral geometry, then you can recover really the metric itself. Okay, you can look at things you can take different views. For example, in some books you read that for example, the Laplacian determines the metric. So this is a completely obvious statement, because if you know the Laplacian, well, you can take two views of it. If you know the Laplacian, then you know the expression of the Laplacian in local coordinates, and then the higher order terms, they are just the inverse of the Riemannian metric. Another way of saying that is that if you know the operator, then you can compute its principal symbol, and the principal symbol is just the metric on the cotangent space. Okay, so, but asking to know the Laplacian is a little too much. Okay, so anyway, so you have this. Okay, so I will skip something, but that I would like to mention. An application of these embeddings, which I will maybe explain here, that's easier, is to give an answer to a problem that was posed by Yao. And the question is, there is this classical result of Courant which tells you that if you take an eigenfunction associated with the nth eigenvalue, when you look at the eigenvalues in increasing order and with multiplicities, then this eigenfunction cannot have more than n plus 1 nodal domains if you begin at 0, otherwise that's n. So n plus 1 if you begin by lambda 0. So nodal domains are the connected components of the complement of a nodal set, of the zero set of an eigenfunction. Well, it turns out that if you don't consider if you look at least at the second eigenfunction, then it must be orthogonal to the constant, so it has to vanish. So it will have at least two nodal domains. And in fact, you can prove on the sphere, for example, on the two-dimensional sphere, you can prove that in any eigenspace, you can find a function with only two nodal domains. And if you are on a three-dimensional sphere, then that's at least with three nodal domains. So you cannot have a bound from below on the number of nodal domains. Now, if you think at the in one dimension, if you look at the Dirichlet problem on an interval, then it's a well-known fact that you can, if you have an eigenfunction, then you can know the number. The eigenfunctions for the Sturm-Liouville problem, they are simple. And if you look at the number of either the number of zeros or the number of nodal domains, then you can determine the order of the eigenfunction. So this led Brünig to look at the length of the nodal set, because here, if you count the number of zeros, that's the length of the nodal set. So here, for example, if you apply Crofton formula, what you have is the following. So you take an eigenfunction, and it has a zero set. So we write the zero set like this. Now what you can do is intersect this by hyperplanes, and you can now vary the eigenfunction. So the idea is that you take an eigenfunction here, and you view this eigenfunction as a linear combination of these eigenfunctions. So how you parameterize your eigenspace. And to compute the volume, so you say that you have something in the sphere, and to compute the volume of a n-1 dimensional set in the sphere, what you can do is intersect this set by hyperplanes, compute the volume of the intersection, and integrate with respect to the hyperplane, and you will have a mean volume. So you can do this here using this embedding, and then you can show that the mean value of, with respect to this variable A, of the volume of a nodal set of eigenfunctions behaves like the volume of M times the square root of lambda. Okay, so this gives you this result, and you can do the same thing here, not for eigenfunctions, but you can do this for if you take many eigenfunctions and you take linear combinations of eigenfunctions which will appear with different eigenvalues, but then you can do the same kind of thing. Instead of embedding by using this embedding, you can use only the eigenfunction, and you normalize in such a way that you get in the sphere, and you can make the same argument, and then you have the mean value of some nodal set, not really of eigenfunctions, but of a linear combination of eigenfunctions. So that's an application that one can give of this theorem. Okay, so now, just before going to the slides, let me explain another theorem which appears. So we'll erase this. This is stated as a lemma in a paper by Ovsjanikov, Merigot, Memoli, and Vibas. And this tells you that that's the following. So that's a sister, somehow that's a sister version of this. So I will consider two manifolds, complete, connected. I need connected here, closed, connected. And say F is C1. And you assume that Km of Txy is Kn of Tx, Fx, Fy for all T positive Xy in M. And the conclusion is that F must be an isometry. Well, this in fact is. I mean, that's easy to prove. So I will do it rapidly. But well, I did not see this kind of result before this paper. So it seems that people in spectral geometry maybe had not realized that there was this result, which is somehow very simple-minded, but that's very nice. So the idea is as follows. So if you look at this, first of all, you can look at this expansion here, and this tells you that the dimension must be the same. Okay, so that's the first thing. The second thing is that you have to use a deep theorem by Varadan, which he also calls lemma. So let me. And it tells you the following. I mean, if it tells you essentially that you can forget this, and you only look at this. You take the logarithm of this, you multiply by t, and you let t go to 0. And so that's obvious on this first term that the limit when t goes to 0 of t log of k txy is minus 1/4 of d squared xy. Okay? So that's obvious if you look only at the first term, and that's not obvious if you want to prove it generally. Okay, so what this tells you is that if you apply Varadin's lemma, so this will tell you that the distance in M between x and y is the same as the distance in N between f of x and f of y. And of course, this will tell you that f is a local isometry because you have this, and because of connectedness, this will tell you that, in fact, this is surjective also. So you have an isometry. So somehow this tells you that if you know the heat kernel, then you know a lot of things. Okay, so there is another property. Maybe I want to show the slides, and maybe I will come back to this property later on. So this is what they call the multiscale property. So let me go to the slides here. Okay, so I essentially said everything except the multiscale properties. So, okay, so the idea is to look at shapes. So for the geometer, shape is a closed surface, closed connected surface. If you think in terms of geometry processing, for example, this will be a mesh. The surface will be represented by a mesh, or maybe by points, only by points. And what they want to do, I mean, that's what I understand of the subject, so maybe Jovan will have to correct if I didn't understand correctly, but what I understand is that what they want to do is make shape comparisons. And for example, they want to make the difference, I mean, to identify symmetries in two shapes which might be in different poses. So for example, if I do this, I should be more or less symmetric. And if I do this, I am not extrinsically symmetric, but my intrinsic body is still symmetric. Okay, so they want to recover intrinsic symmetries in some shape representation. And they want to detect some features in the shapes. Okay, so let me try to illustrate this. So here are two shapes that they are their favorite, the favorite shapes with which they experiment. Okay, so for example here, that's exactly what I did earlier. I mean, you have two shapes, the same shape, but with two different poses. And for example, they want to detect the symmetry, and they want to, you see, you have the red lines here, and they want to be able to detect these red lines even when the body has a different posture. Here, for example, you have the dragon, and you would like to identify what the pose of the dragon are. So you would like to identify these 4 points, for example, 1 to 4. Or here, another, the same, I mean, two different poses of the same shape. Okay, so that's essentially, I mean, some of the problems, of course, I mean, the people can ask. Now, in some papers, I mean, some people realize the importance of eigenvalues and eigenfunctions to understand shapes. And apparently, I haven't gone too much into the data sets, but apparently this came first in the data set community, where they realized that when you represent a data set by a graph, you can do an analysis like statisticians do by looking at the principal direction analysis, something like this. But you can also look at the combinatorial, the graph, the combinatorial Laplacian, and you can look at the eigenvectors of the Laplacian and project your data on the space generated by the first eigenvectors of the graph Laplacian, for example. So these pictures I took from in a paper of Levy in 2006. So here is the armadillo, and then they have a mesh, so they can compute the Laplacian, they can compute the eigenvalue, they can compute the eigenfunctions, and then they take the position vector and they expand the position vector in the expansion by eigenfunctions. Okay, and then they take only 10 or 20 or 40 eigenfunctions. They cut the series and they look at the corresponding shape. So somehow you see that, of course, I mean, you can expect that when you take many eigenfunctions, then you will recover the shape. This is just that the set is complete. But still, when you take a relatively small number of them, then you see that you can recover something of the shape. Not the shape precisely, but at least something of it. So here is the similar picture where they represent the normal vector of the rabbit. And so you see that first it looks very, very flat, and then you see some extrinsic geometry somehow. Okay, and now there is another picture which I think is really very striking. So what you do here is that you have your two shapes, and you compute the eigenvalues, eigenfunctions. You take the position vector. You make this Fourier analysis of the position vector for each of the two shapes, and now you take the 6 first coefficients in the armadillo, and you transplant these coefficients to the eigenfunctions of Homer, and you see that when you do that, then Homer takes the pose of armadillo. So it really seems to show that the eigenfunctions, they really carry a lot of interesting thing on the geometry, even if you take a very small number of the eigenfunctions. Okay, so what they try to do, they want to introduce signatures to characterize shapes as much as possible. I mean, they obviously know that it might not be possible to characterize exactly, but to get as much information as possible. One possible way to do that, for example, when you have a mesh, is to take 2 points of the mesh and compute the geodesic distance between these 2 points, and then you have your mesh. You construct a big matrix of the mutual distances, and you can try to make analysis of this. Okay, so what is in gray is something I didn't really look into. So what they claim is that this is time and memory consuming, so let me forget it. But they say that's very noise sensitive, and we'll see that in a minute. So another method is to base the signature on eigenvalue and eigenfunctions. Okay, so for example, here is an example Ristamov introduced what he called the GPS for the global point signature of a shape. And what he does is that the GPS of a point is just, you look at the values of the eigenfunctions. The functions, of course, that's always orthonormal. But then you also plug in the eigenvalues. So you rescale your eigenfunctions. Okay. So in fact, you should recognize the green function behind this. Okay. So somehow you have the green function. Okay. So for example, in this paper by Ovshanikov, Sun, and Gibas, they devise an algorithm for symmetry detection based on this signature. Okay, so for example, these pictures come from their paper, so there is an algorithm behind this. So for example, they are able to do this, and here they have several shapes, and the red lines here identify symmetries that they get through this signature, through this GPS. Okay, so here you have something which is very interesting, in that in a shape you may have some noise, and for example, the noise here is a small bridge between the thumb and the forefinger. Here in the first shape on the first line, and on the right, this is a small bridge between the hand and the hip. Okay, and now they take the shape without the noise and the shape with one of the two noises, and they apply their method. And although the two shapes on the top are not symmetric, they still recover the symmetries, because the method just forgets the noise. Okay? So I will come back to this later on. Okay. So now maybe I would like to explain now something. What an interesting feature is that what they claim is that now they consider essentially the heat kernel. So now we will consider essentially the heat kernel and not the green kernel as above. So the idea is here you have an extra parameter which is the time, and what they claim, which I don't really understand, but what they claim, and is that t is a multi-scale parameter. So you can explain this in several ways. For example, here you can look at what happens when t goes to infinity. Of course, when t goes to infinity, if you where is that? Here. If you look at what happens when t goes to infinity, you will kill everything except lambda 0. And then the eigenfunction is constant, and what you get is 1 over the volume. So you have a rough idea of the global geometry by just knowing the volume. Now, if you think at this, for example, this first term, you see when x and y are different. Well, this term just bothers a little bit, so we can forget about this term by doing the following. Let me write this here. So you can look at ktxy, and you divide this by z of t. So z of t is this. So the behavior when t goes to 0 is the same power of t. So somehow you kill this term. So now you see that when t is big with respect to the distance, then somehow this term will be very small, and you will be something which looks like a constant. When t goes to 0, if x and y are not equal, then you see that you will have something which decreases exponentially. Okay? So somehow it tells you that t should allow you to look at different scales. Now, there is another interpretation for this. If you take a complete non-compact manifold, then you have a result of Gregorian, which tells you the following. If you have a manifold whose volume grows like r to the alpha, then essentially at time t, let me tell it like this. Essentially at time t, so you have the Brownian motion, which you can introduce the Brownian motion essentially using the heat kernel. So you look at the probability that a path issuing from x will be somewhere at time t. And so what Gregorian tells you is that there is the probability that the path at time t be outside the ball of radius, a constant radius square root of t log of t is 0. So essentially this tells you that let me say it differently. The probability that the particle at time t is within the ball of radius with center x and radius square root of t log of t is 1. So somehow this property here tells you that heat propagates at infinite speed, because when t is positive you have heat everywhere, very little, but you have heat everywhere. And what Gregorian's result tells you is that somehow, in fact, there is a finite propagation speed, because in fact you will stay at time t, you will be in a ball of radius square root of t log of t. Okay, so that's another interpretation of the multi-scale property. So it tells you that when you look at different values of t, you should be able to look to see either small behavior or small scale behavior or large scale behavior. But this, I think, is something that we should explain mathematically more. So this is something here. You look at the expectation of the geodesic distance of the Brownian motion to the point x, and you see that here that's somehow the expected law, the yellow curve, that's t log of t, square root of t log of t, and below you have what happens at the different points in on the shape. Okay, so what these people do is that they introduce what they call the heat kernel signature, which is just this function. Or they scale it by dividing by z of t. And now you have a very nice, very interesting behavior. Okay, so here is, they computed the k of txx on these shapes. And the red is hot, and the blue is cold, and this corresponds obviously to this term here. So when t goes to 0, you scale, but when the curvature is positive, you have something which is bigger than when the curvature is negative, and this explains the colors. Okay, so this is just okay. And so what experiments show, let me say, is that if you look at this scaled HKS, heat kernel signature, then this allows you to discriminate between different points. So for example, if you look at the dragon and you have these 4 points, 1, 2, 3, 4, and you would like to discriminate between these points, and then you look at the signature, in fact, the scaled signature. And so at these points. So you see that for time short, I mean here there is the scale is log t in the time, but for time small, then you see that the 4 points have the same signature. So you cannot see the difference between the 4 paws of the dragon. Now if you look at time much bigger, then you see that you separate the front paws and the rear paws. And of course, I mean, if you think in terms of neighborhoods, you see that the neighborhoods of the rear part are different from the neighborhoods of the front part. So somehow this explains why this behavior is like that. Okay, and I think that would be nice to have a theorem to really explain this behavior. What did I do here? Yeah. Okay, so what they did, which I think is quite interesting, they made an abstract model. So they have this shape, and they consider these 4 points, and they look at the behavior of the heat kernel signature at these points, and then again with this varying t, again with this logarithm scale. So you see, first of all, that the scale, the signature is the same for t small, and it's easy to understand that because the neighborhoods of the points are essentially the same. For t small, if you are in 1, 2, 3, or 4, you don't see what happens at the other points. And as t grows, you see that you have a difference between 1, 3 and 2, 4. And when the size of the neighborhood increases, then you see that the neighborhoods of 1, 3 or 2, 4 are different. And now if you let time evolve a little more, then what happens is that you have a difference between 3, 4 and 1, 2, because the neighborhoods, when you take a neighborhood of 1, 2, then because it's at the end of the bar, then you see that the neighborhood comes back, and that's not the case in 3, 4. Okay, so again, I mean, this experiment shows that the heat kernel signature is able to discriminate between these 4 points, and okay, that's my time is over. So that's all the pictures in this thing. So they have a theorem, And this theorem tells you the following, in fact, that if you look at this heat kernel signature, then it allows you, that's a similar result to this one, it allows you to determine if F is an isometry just by looking at the value of KTXX and KTFXFX. But for this, they need an assumption, and the assumption is not nice because they need the manifolds to be generic, and generic means, in fact, that the spectrum of these two manifolds is simple. Okay, so essentially what you do is the following. If you write K of TXX, so this is this. Then the first argument is because this series converges uniformly, then if you know this function, then essentially you know these numbers and you know these numbers. Okay, because you look at the behavior when t goes to infinity, and then you can discriminate the points. You multiply by e to the lambda t kt xy, for example, and you look at what happens when t goes to infinity. So if lambda is less, let's say, if lambda is negative, you will be 0. If lambda is equal to 0, you will get 1. So somehow this determines that lambda 0 is 0. Okay, so you can forget lambda 0. So let me begin by 1. So now if lambda is less than lambda 1, you get 0 when t goes to infinity, and if lambda is exactly equal to lambda 1, you get something, well, let's say, you get something positive. Well, the function could vanish, but let's just forget this for it, okay? So somehow this tells you that if you know this function, you will be able to determine the eigenvalues just by testing the behavior of the function at infinity, and you will be able to know these functions. So somehow this tells you that you know, knowing k, you know these values. But because the spectrum is simple, this tells you that you know the eigenfunction up to sign. And then you use the fact that the zeros of an eigenfunction, when you cross the zero set, then here, if you are positive here, you must be negative. And then this will tell you that you know well how the sign changes, and then when you apply this with t, this will tell you that for all eigenfunctions, you will have an eigenfunctions of m at x will be the eigenfunction of n at f of x, with a plus or minus which will depend only on the point x. And then you can plug this in this formula, the change of sign will disappear, and then you will be able to apply this theorem. Okay, so just if you, okay, let me just, okay, you can do something else by just fixing a source P, and they have another similar theorem, and they use that for symmetry identification. Okay, so here is, for example, symmetry identification. So the idea is that when the spectrum is simple, if you have an isometry, if you have a generic manifold in the sense that the spectrum is simple, if you have an isometry, then the isometry is completely determined by the image of one point. If you know x0 and f of x0, you know the spectrum is simple, then this determines the isometry completely. Okay, so they somehow imagine that they already know that one point, one correspondence, and then they are able to construct the other correspondences. Okay, and this picture, for example, shows that this is not quite true. And of course, the reason is that the generic assumption is not really reasonable. And for example, the difference between the first two, here the first two is on the left. You don't see one of the arms, and this because you have only one correspondence, and if they give two correspondences a priori, then they are able to determine the arm. So this tells you that probably if you know enough, if you have enough points, and you know k of t, pi for these points x, then you will be able to determine really the isometry. So to determine an isometry by the heat kernel, you will only need a finite number of correspondences of points. Okay, so for example, this theorem I mentioned here. So if M is not generic, if M is not generic, this theorem is not true. It's sufficient to look at the sphere to see why the theorem is not true. But what the idea would be, if you take x0, x1, xn given points, and if you look at the map, instead of taking only one source point and taking n points, then probably you should be able to get an injective map. So I mean, the idea would be to have a theorem that would hold in more generality than generic, which is not a reasonable assumption. Okay, so yeah, I think that's just to explain this. The idea is that the heat just forgets the small tubes, and there is a theorem by Collet-Tanné which tells you the following. If you take a manifold like this, you take 2 points, you take a curve, and now you take a small epsilon tube. You look at the spectrum. When epsilon goes to 0, in fact, the spectrum of this object will converge to 2 spectra. First, the spectrum of the manifold without the handle, and then so here you will have your manifold, and then you will have, if you put here length L, then you will have the spectrum of the interval with the Dirichlet problem. This is when epsilon goes to 0. Now, if you put a small handle, the idea is that this length will be very small, and so the eigenvalues, this spectrum here, will be very big. So somehow you don't see the first eigenfunctions, they essentially don't see this small bridge. And this is why you can see this stability under small perturbation. I mean, small in some sense, but I mean a big perturbation in terms of topology. Okay, so sorry, I just passed the. Okay, thanks.